That's right. Senior skip day was on Friday. That's right. Or sick day. Ah, there you go. Sick, not skip. There you go. Yeah, I know. That was a quick. I'm so glad you don't have pneumonia any longer. There you go. Okay, so we have some vocabulary, some examples. I'm going to go ahead and give you about a minute or two on each slide to go ahead and copy those down. But this symbol right here, okay, that is the Greek letter sigma. That is what we use in math for summation. So for series, we are going to be adding terms of a sequence. That's what a series is. Okay. So summation notation is the sum of the terms of the sequence denoted as that right there. Okay. Series, yes. Arithmetic and geometric series. Oh. We're not talking about pairs of combinations, no. That's something different, yes. Oh, okay. It's right here, look. What is it? Oh, is that a tiny remote control car? Yeah. Nice. Can we just watch you play with the car the whole class? That would be cool, but we got some work to do. That would be very nice. That would be very cool. All right. We are talking geometric and arithmetic series. Okay, so a series is when you go ahead and start adding the terms of a sequence. Okay. And you'll notice the lower boundary, it could be k. Typically, that's what you have. You could also use the variable n. But the bottom number tells you what term you want to start at. The top number tells you what term you want to end at. So like that example there, I would like to add the first 7 terms of the sequence. And you'll notice the formula to get the terms, well, this one's k squared. So I plugged in 1 squared plus 2 squared plus 3 squared, dot, 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 all the way to 7 squared. Okay, that's the difference between a series and a sequence. A sequence is just a generated set of numbers. Okay, it has some kind of pattern to them. But when I start adding the terms in that sequence, then we call it a series. Okay. You drew that sigma notation well? All right. So like the next one here, you'll notice I want to find the sum. I want to start from the second term and stop with what? Oh, not 4. The 9th term. The lower number is the term you want to start with. The upper number is the term you're going to end with. And here, the expression to get the terms would be 4k. So the second term would be 4 times 2. Plus, the third term would be 4 times 3. Plus, fourth term, 4 times 4, all the way until I got to the 9th term. 4 times 9. There you go. If there's no ending, there is a way to add what we call an infinite series, but there is a specific rule that has to be followed for that to happen. So we'll probably be looking at that in a day or two. Okay. I'm also thinking tomorrow would probably be a good time to go ahead and have a little quiz over sequences, the homework you just turned in. Okay, so tomorrow I'll pass back your homework. We'll go ahead and finish with the quiz tomorrow, and we'll just keep looking at series. Hopefully we'll be able to finish it this week. If not, then we'll continue next week. Binomial theorem is the next lesson after this one. Why is tomorrow going to be a stressful day? Oh. So you mean like next Wednesday? Next week period's going to be stressful. Okay. Oh, I hope so. I hope so. Okay. So a geometric series is the sum of all terms in a geometric sequence. An arithmetic series is the sum of all terms in an arithmetic sequence. And then, of course, an infinite series is one in which an infinite number of terms are added. So there your upper boundary will be the infinity symbol, the sideways 8. But again, there's a special condition that has to exist if you can do that. You can only do it for geometric. You can't add an arithmetic infinite series. Okay. Is everybody done with this first slide? Okay. So here's the second part right here. A finite series is one in which a finite number of terms are added. A partial sum is the sum of part of a sequence. And then I got some examples there. Okay, so before I go ahead and start looking at them, I'll let you take about a minute to jot those down. How was what? It was good. I mean, I liked it. I'm probably not going to rate it as high as some people. I would probably give it maybe a 7. Now, I will go ahead and say this. It was a good movie. The third act where you have the big battle at the end that combines everybody, I would say that was amazing. It was very well done. It's going to be very, very difficult to, top that if it's ever done. But I don't know, some things really stuck with me about the movie that I just couldn't get past. Like, for one, I mean, it's 3 hours long. I'm not going to spoil it. I'm recording, so I'm not going to say anything about it.
The part that really got me was like, love you 3000.
I love spoilers.
You love spoilers? Oh.
I'm like the one person.
I told you to put it in, but you don't listen. Well, I mean, you should have told me before.
Did you like it? I mean, it was a good movie. Don't get me wrong. Yeah.
I started crying.
My wife did too.
I felt bad for the guy sitting next to me because, like, it was one of those cries where you try to hold it in because you're in a movie theater and you can't, so it starts driving you to.
Yeah.
The guy next to me probably thought I was having a panic attack right now.
My wife did. I mean,
I could not breathe.
I will say that, I really didn't tear up during Infinity War, but I did kind of tear up in this one because Stark's daughter is very close to my daughter's age, so I can kind of relate in that fashion. So that's not any spoilers or plot points given away. That is it? Oh, you already told him?
Yeah.
Okay.
The thing is, that already got spoiled for me by Ricky, because Ricky just sucked.
Yeah.
Baby, when I watched, like, I literally went
Okay.
The girl beside me, she got back and she was like, stop. She was like,
I'll be like this.
And you know what was insane to me? I heard that, I don't know where it was across the country, but I read this on IMDb, that people bought tickets ahead of time and then were selling them on eBay at ridiculously higher prices because people were willing to pay them to see them on opening day. Like, a pair of IMAX tickets went for $15,000 on eBay. And I'm like, just wait a few days. I mean, I think you're going to have buyer's regret. Like, a week down the road, you're like, wow, that was a good movie. Was it $15,000 good? Probably not.
Mr. West, I had buyer's regret. But
Why's that?
I bought like $18 paper.
Oh, did you?
Yeah, I bought it for like $18 worth of paper,
Yeah.
like 2 weeks ago on Amazon. And then like, it's coming in today. And then
Yeah.
now that I remember that I bought that, I'm just like, I was hungry like 3 days ago. And like, I had no money in my bank
Yeah.
account. And I was just like, wow. That's probably
Okay.
Is it like really good paper though?
Well, I mean, I guess it's fun. You know, it really is fun if you can see it in a packed theater where the crowd really gets into the movie, you know, and they cheer and they do all that. That can be fun, but that's not what I go to a movie for. You know, it's,
Don't bring your kids.
yeah. And, you know, someone yesterday, this is like the cardinal rule of movies. Someone brought a baby. This baby had to be, excuse me, there's no way this baby could have been more than 6 months old. And, of course, you're going to bring it to a 3-hour movie. Now, I saw these people walking in. My first thought was, what are you doing? You know, And they had to take the baby out several times because, of course, it starts crying. Because that's what a baby does. You know, a baby, if it needs something, a baby is going to tell you it needs to be changed. It's hungry. It can only do so by crying.
But the baby's in here for like 4 hours.
Oh, my God. Find something else. Yeah, go real fast. Okay, but anyways. I say the movie was good. You know, maybe when I'm not recording, I'll go ahead and give you my opinions on it. I don't want to, no spoilers. Okay. But Infinite, the one thing I did go ahead and write here, you'll notice for this example, I want to start with what term? The third term, and I want to stop with the what? The sixth. You want to be really careful because the number of terms you're going to be adding up, it's not always what you think. Like, for example, if you want to go ahead and find the number of terms between 3 and 6, your first idea might be to go ahead and subtract those, right? Okay. Might be to subtract them. But 6 minus 3, you're not adding up 3 terms. Because think about it, if you start at 3, 4, 5, 6, there's actually 4 terms. Okay, so there's a formula that you need to use if you're not starting with the very first term. What you want to do is take the upper value minus the lower value, and then you add 1. Okay, because see, if I go ahead and take 6 and subtract 3, I'm subtracting off the term that I wanted to start the series with. That's why we add the 1 back to it. So if I were to give you something like this, let's say, oh, that's a horrible circumcision. Okay, like this here. Let's say we start with n equals 5, and I want to go to the 11th term. Okay, how many terms am I actually adding there? Okay, well, let's see. Take the difference. So what's 11 minus 5? 6, but then you add 1. So I'm actually adding 7. And if you actually list out the terms, that makes sense. 5, 6, 7, 8, 9, 10, 11, and you'll notice there are 7 terms there. The only time that that upper number is the actual number you're adding is if you start at the first term. If you don't start at the first term, that's when you want to go ahead and maybe write it out or use that little formula here. Okay. And then this last one here, a partial sum, is the sum of part of a sequence. So you'll notice this one here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, it would just continue, right? Okay. So a partial sum is when you would only add a set number of terms from the sequence. That's what we're referring to when we say series. Okay. So we're going to go ahead and start off with the easier of the two in arithmetic series. And there's 2 formulas here. Okay. So S sub n equals n divided by 2 times a sub 1 plus a sub n. So n is the number of terms you're adding. N is the number of terms that you're going to be adding. A sub 1 is the first term. Okay. A sub n, that's the last term. Okay. So for either case, if you want to use a formula, you do have to absolutely know the number of terms you're adding up, and you have to know what the first term is. Beyond that, that's where the 2 formulas get a little different. Okay. So if you know the number of terms, the very first term, and the last term, you're going to want to use the first formula. Okay, because you've got variables for all of those. But you'll notice the second formula, you still need to know the number of terms in. You got to know the first term, and what else? What's another variable in the second formula? D. What does that D represent for an arithmetic sequence? Not distance. It's the common. Ooh, that's a good one, but it's not the common denominator. Common difference. Or the distance between the terms. Okay, that's a good way of putting it. The common difference. Okay, there you go. Now, there is one other thing we're going to change as we go along. And you're going to notice this. When you see S sub n, that's a partial sum. Let me go ahead and write this right here. That's going to be a partial sum. That means that you're going to be adding a specific number of terms, however many that may be. Okay? But if you just see S If you see S with no subscript, that represents an infinite sum. So both of these right here, these are both partials. Okay. So if I'm adding, for example, 8 terms, then it would be S sub 8. If I were adding 20 terms, then it would be S sub 20. Okay, just like before, that little subscript n is the number of terms I'm going to add up. Okay. Well, let's take a look at a problem. I think we have one of these, and then we get right into geometric series. There's more about geometric series in this lesson than anything else. Okay, so example 1. A corner section of a stadium has 8 seats along the front row. Each successive row has 2 more seats than the row preceding it. If the top row has 24 seats, how many seats are in the entire section? Okay, so let's think about what this sequence would look like. Okay, each row is a term in the sequence. Okay, so for example, the first row has how many seats? So it has 8, comma. Now, how do we generate the sequence? What's it telling me? Each successive row has 2 more seats. So if the first row had 8, the second row would have 10. Then the third would be 12. And this is one of those ones where you might, it's small enough, you could probably just go ahead and go all the way to 24. So the fourth row, 14, 16, 18, 20, 22, 24. So that's the sequence. Okay, that's a sequence if we just generate the numbers in order. If I go ahead and start adding them up, remember that's when it becomes a series. Series means I'm going to add the terms. Well, what do you think the first term is? 8. What's the common difference? It is 2. Now this one was small enough that I went ahead and just listed it out. So it looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. So I know that the 9th term, the 9th row, is going to have 24 seats, right? Now remember, you can also use the formula we had from the previous lesson to go ahead and figure that out, because what if it said, it went to the 100th row? You really don't want to sit there and probably list all of these out, right? That's way too much to go back and add up. So the formula would be very useful to you. The formula was a sub 1 plus n minus 1 times d. Okay. Let's say we're trying to figure out the number of terms that we're going to be adding up. Okay. Well, we know that the number of seats on the last row is 24, right? So I'm going to say 24 equals, what was the first term? 8 plus n minus 1. And what was the common difference? 2. All right. Hey, there we go. Okay, so now all we need to do is just go ahead and solve this for n, and that's where I'm going to get the 9 from. I know that I'm adding 9 terms in this sequence. Okay, so how would you continue to solve this problem here? Okay, I'd go ahead and start with a D. Distribute, she's absolutely right. So 24 is equal to 8 plus, that would be 2n minus 2. So 24 is equal to, what's 8 minus 2? Plus 6. Okay. Now what? Okay. So go ahead and subtract the 6. Those cancel. 24 minus 6 is 18, which is equal to 2n. So n is equal to 9. See, I was able to get 9 terms. So you could still use that formula we had previously in order to help you find missing items. Oh, I'm sorry, I made a mistake here. N is 9. The last term is actually 24. That's my fault. Okay? Because the number of seats is the actual term value. Okay, the row number is the term number. Okay. Well, it looks to me like I have the first term. I've got the common difference. I know the last term. I even have the number of terms. So if I were to come back over here, which formula could I use? Actually, could I use either? Yeah. I've got the number of terms, the first term, and the last. But I've also got D. Yeah, if you have a choice, I would probably go with the first one just because it's way easier. Okay. So let's see here. S sub n would equal, it's n divided by 2 times a sub 1 plus a sub n. So we're adding 9 terms. So S sub 9 equals, remember, so n equals 9, right? So that's 9 halves times, the first term was 8, plus the last term, the 9th term, was 24. Okay. So let's see what that ends up giving. 9 halves. Let me go ahead and take this off real fast. That was the previous one. So control divide. I'm going to go ahead and say 9 over 2, or you could type in, 4.5. And then 8 plus 24. Okay. Exactly the formula that we just had. I push enter, I'm getting 144. Okay. Now, if you were to do it the old-fashioned way, just add up the terms you saw. Remember, we started with 8, and every row increased by 2. So 10 plus 12 plus 14 plus 16 plus 18 plus 20 plus 22 plus 24. See, it still gives me the same thing. Okay. So if it's small enough, maybe you can just go ahead and add them up if that's what you want to do, but the formulas will give you the same answer. So I know that section should have 144 seats. There we go. Is everybody okay with that? Does that make sense? Okay. That's what we refer to as a series, when you start adding the terms of a sequence. Okay. Well, let's take a look at some formulas for a geometric series. Now, this is where we're going to go ahead and change it. You see how it says S sub n? That is not correct. Okay. Well, not for that. I'm sorry. For this one. This should just be S, because that's an infinite sum. This other one, S sub n, that's good. That's fine. Okay. So remember, S is an infinite sum. S sub n is a partial sum. Okay. Well, let's see here. You're going to need to know the number of terms. You need to know the first term. And what's R? That's the common what? No, that's when you're adding the term, the common difference for an arithmetic sequence. But for a geometric, remember, that's what you multiply over and over again. That was the common ratio. So R is the common ratio. There you go. Okay. And now there's the formula if there's a infinite geometric series where up on top you have the infinity symbol. Okay. The one restriction I was talking about, the absolute value of that common ratio has to be less than 1. Okay. So if the absolute value of your common ratio is greater than 1, you cannot use this infinite sum formula. And the formula itself is very simple. You simply take the first term and divide it by 1 minus R, the common ratio. Okay. Well, tell you what, we got 1229. Let's go ahead and stop there, and then we'll go ahead pick up here tomorrow.